Compounds part 5. Hope all of you are doing good, sound and healthy and taking care of yourself. So let us move on to this uh, next theories pertaining to coordination compounds. So in the previous class we have seen Werner's theory, and Werner has proposed the geometries of coordination compounds with the octahedral and square planar, just to see how the octahedral and square planar geometries would look like. So in that, octahedral would look like something like this. So where the central thing that you are looking at, whatever the central part that you are looking at, is your cobalt plus 3, and imagine these are satisfying your primary valencies. These chlorines may be, the green parts are chlorines, and NH, these are NH3s. The blue one with the white balls is the NH3s. That's how hexa coordination can be represented. And he has even given the cis structure and trans structure. So just have a look at these two green chloride ions you can imagine as. So these two green parts are at the 90-degree separation. Even you can arrange that one at 180-degree separation. If you arrange that one at 180-degree separation, then it results in what? Trans structure. As these are at 90-degree separation, you can say this is cis structure in that case. So this is pertaining to trans, wherein the two greens are what? With maximum distance or angle of separation, that is 180. So you can say this is one of the trans structure of hexa coordinated molecule. Okay, so octahedral would look like something like that. So where the pink part is what? Your central metal atom or central metal ion, and the blue, the white one you can say as what? Hexa coordination, where it is representing octahedral structure. And tetrahedral would look like something like this, where the pink part is central metal atom or central metal ion, and these white parts are what? Coordinating through what? Coordinating ligands, you can say. So that's how your tetrahedral would look like, and the square plane would look like something like this. So he has given geometry of that. Basically he has given this geometry, for which he was even awarded Nobel Prize in 1913. So Werner has proposed the geometries of these coordination compounds, for which he has been awarded, or is bestowed with that Nobel Prize. So we should be very thankful for giving the coordination compounds geometries to Mr. Werner. Okay, so anyway, this is square planar structure. He has given that one in the case of platinum coordinated to what? Chlorines, you can imagine. The central metal atom is platinum, and these are chlorines, you can imagine as. Okay, now where else he could not explain? What are the parts where there is some lack, you can say. So though it is given some 100 years back, still we can go back to that time and you can say that Werner hasn't explained these things. So that limitation part usually will be asked in examination. For that sake we are giving. Otherwise Werner was awarded Nobel Prize at that time, which means that very good contribution then, but still we can say some limitations were there, that it could not explain the magnetic properties, color properties or optical properties, interaction of light with that coordination compounds he hasn't answered, or on interaction with light what kind of color it is the coordination compounds are exhibiting, and what is the reason behind that he hasn't explained. And even the magnetic properties of coordination compounds also, and why there is only limited to 6 ligands, why they are approaching towards your central metal atom or central metal ion, why not something more than that, that also he hasn't explained. So directional nature of this coordination bonds, or coordinate covalent bonds, also he hasn't explained. So some stability of that with respect to that, why tetrahedral or square planar are less stable compared to octahedral, are the stability aspects of that one in terms of energy he hasn't explained. That you can write as what? Limitations of Werner's theory. So that it has failed in what? Explaining magnetic, color and optical properties, and Werner's theory couldn't explain what? The reasons why certain elements don't form coordination compounds, why only certain compounds are forming, that also he hasn't explained. And has plainly explaining what directional property of coordination compounds, wherein why the bonds are coming in a square plane in those directions only, why not in some other direction, that he hasn't explained. Okay, so that you can say will be explained in later theories. Okay, So directional nature of these coordinate bonds also hasn't explained, and we still could not explain what energy aspect, which in turn relates to what thermodynamic stability of the complexes is not explained by Werner. You can say them as, if it is not explained, you will write that one as what limitation of that uh, theory you can write as. And then comes up the electronic interpretation. And the electronic interpretation of these coordination compounds is given as a theory that is proposed by Sidgwick. It is called as Sidgwick's theory. And if someone says Sidgwick's theory, which means it is electronic interpretation of coordination compounds, which is given in one single word, that is EAN. He just tried to explain the formation of coordination compounds in terms of electron pairs being given by certain ions or neutral molecules which are having excess pairs of electrons. They will give electron pairs, and the central metal ion or central metal atom will tend to accept these electrons. How long they will give these electron pairs is answered by what? A theory that is called as Sidgwick's theory. Why these are giving electrons, and why some metal species or some metal ion is accepting electrons, that is answered by what? Sidgwick's theory. It is simply that these ligands will try to donate electron pairs. They will try to donate electron pairs to what? Your central metal. They will try to donate electron pairs. How long this central metal atom will accept electrons? As long as it is what? Not satisfying what? That inert gas configuration. If it is not satisfying inert configuration, it will try to accept electrons. Once it is attaining that inert gas configuration, it will what? Obviously stops accepting electron pairs. The central metal atom or central metal ion will keep accepting electron pairs from these ligands from all directions, and it will accept electron pairs till it gets what configuration? Nearest noble gas configuration. That's what Sidgwick's theory is, and that is given in terms of what? Effective atomic number. The total number of electrons is called what? That total number of electrons the central metal atom or central metal ion attaining is given as a number that is called as effective atomic number. That's what is Sidgwick's interpretation. This electron pair acceptor and electron pair donor will be there, and the donor is what? Your ligand, and acceptor is your central metal atom. Accepting occurs till the nearest noble gas configuration is obtained by the central metal atom, and donation happens till the ligands are keep donating as long as or until that central metal atom or central metal ion attains the next nearest noble gas configuration, you can say as. So that's how you can say that's your attaining nearest noble gas configuration. That's Sidgwick's theory. Okay, right. Then comes up, what is this EAN? EAN is what? How it is calculated is the central metal atom's atomic number you will take Z minus oxidation state of that metal plus twice the coordination number. It's given as EAN, effective atomic number, is equal to atomic number of that central metal atom or central metal ion minus oxidation state of that metal if it is an ion plus 2 times the coordination number. So if the calculated EAN value, whatever value that we obtained by calculating EAN of that metal, if it is equal to the nearest noble gas configuration, that is usually transition metal, if you take the nearest noble gas configuration will fall at 36, 54 and 86. 36 for krypton, 54 for xenon and 86 for radon. So if that central metal atom is attaining this configuration through its oxidation state plus twice the coordination number, then it will attain stability. That's what is Sidgwick's proposal. So if sometimes it may not also, then you can say it's not following Sidgwick's theory. If it is not attaining that, you may say that the complex is less stable. So you may say some aspect of stability is answered here, that if the central metal atom is attaining that effective atomic number of nearest noble gas configuration, then you can say that it is stable, and if it is not attaining that nearest noble gas configuration, then you say that it is not stable and it is not obeying Sidgwick's interpretation or Sidgwick's theory. So that's EAN. Then, so let us see one of two cases where EAN is given. So let us take FeCN6 minus 4 hexacyanoferrate 2 ion, hexacyanoferrate 2 ion. What is the central metal ion here? Fe plus 2. Ferrate 2 we have written as hexacyanoferrate. Hexa indicates 6 cyanides are there. So hexacyanoferrate 2 ion. This oxidation state of iron in FeCN6 minus 4, here it is what? How much? Fe is plus 2 in oxidation state. So sum of algebraic sum of oxidation states is given there. 6 cyanides will render minus 6 and Fe is not known. So it's minus 6 but written as what? On the top it is written as minus 4, which means Fe is rendering plus 2 charge. So as such, the oxidation state of iron is what? Plus 2. Number of electrons in iron going to its atomic number, it is 26. So but here it is showing plus 2 oxidation state, so number of electrons would fall by 2, decrease by 2, making that one as 24. So how many electrons are there in Fe plus 2? It is 24 electrons. So that's what we arrived at. Now the ligands are donating to Fe plus 2. So ligand, as Sidgwick has proposed, that ligands keep donating to electron to central metal atom or central metal ion till it attains your noble gas configuration. So how many ligands are there? 6 ligands, each rendering 2 electrons, So it makes that one as what? 6 into 2. So that's make that 6 into 2 is 12. So go for EAN calculation. So EAN of Fe plus 2 in FeCN6 is how much? 26 electrons minus 2 is 24, plus 6 into 2 is 12, 24 plus 12 is 36. Therefore, it has attained the configuration of the electronic structure of what? Nearest noble gas, that is krypton. So from that you can say EAN is valid here and the complex is stable and its Sidgwick's theory is followed. You can write all that. EAN is valid slash stable complex, and what else you can say? Sidgwick's theory is followed. Sidgwick's theory is obeyed, you can say, followed, you can say. So EAN is valid and Sidgwick's theory is followed, you can say. EAN is valid in the case of FeCN6 minus 4. So all that you can state. So just to put up in short the formula that we have written. In that form, if you go for writing, EAN here is calculated as what? At atomic number minus oxidation state plus twice coordination number. So atomic number is iron 26 minus oxidation state is 2 plus 2 times coordination number is 6 into 2. That is 36. So the stable L complex as it has attained next nearest noble gas electronic configuration or electronic structure, you can say. So that's how you can say Sidgwick interpretation is simple, that the central metal atom or central metal ion is trying to attain, what is the central metal is trying to attain? Nearest noble gas configuration through ligands binding in different directions. Okay, that's what is electronic interpretation we say. So Sidgwick's theory is simply understood in the form of EAN. So comes up with few examples I have quoted here. Just have a look at. So you just have a look at these metals complexes wherein this was outsourced from some. Okay, what is the complex there? K4FeCN6. K4FeCN6. Oxidation state of metal ion is plus 2, the first one. So number of electrons lost in ion formation is 2. So electrons given by ligands is 12. 6 ligands are there, they will enter 6 to the 12. So you simply put up in that EAN noble gas configuration. So to attain EAN or noble gas configuration attaining, how to calculate that one? Iron is 26 minus 2 plus 12. Iron atomic number 26 minus oxidation state is 2 plus 2 into 6, that is 12, making that one as 36. So attained krypton configuration. Therefore you can say it is stable, EAN is followed and follows Sidgwick's theory. Then second case is cobalt. CONH3 taken 6 times plus 3. So by simple following oxidation state is 6 ligands are rendering 0 charge. So cobalt is in what state? Plus 3 state. So oxidation state is +3. Electrons lost in ion formation is 3, and electron given by ligands is 12, that is 6 into 2, making that one as 27 minus oxidation state 3 plus 6 into 2, 12, that is summed up as 36, which is electronic structure of what? Krypton. Therefore, you can say that this hexaamine cobalt 3 ion is what? Stable complex ion. Okay, and En is followed, Sidgwick theory is followed. Similarly, this nickel complex, nickel tetracarbonyl, 4 CO ligands are there. There the oxidation state of nickel is 0. Electrons lost in formation of ion is 0, as it is neutral atom. Central metal atom is neutral. So 4 ligands are there, 4 2s are 8. So metal atoms atomic number minus oxidation state plus electrons donated by ligands is 8. 28 minus 0 plus 8, that is obtained as what? 36. So as such, again in this case also you can say that nickel tetracarbon is a stable complex, follows EAN rule and obeys Sidgwick's interpretation or Sidgwick's theory. And similarly, this copper, complex with tetraamine copper 1 ion, tetraamine copper 1 ion. So in that 4 amines will render 0 oxidation state. Copper's oxidation state will be +1. 4 ligands 0 and copper is +1, so it's written on top of this complex. So making that one as CuNH3 taken 4 times plus. So oxidation state of metal is what? +1. Electrons lost in ion formation is 1. That is Cu +1. No? So its electronic configuration minus 1 electron we should write. So making that the atomic number is 29 minus 1 plus 2 into 4 ligands will donate 8. So thus making us, so I will try to increase its size. Okay, now it's slightly, I just increase the visibility there. So have a look at. So then comes up with another one. One more complex we are going to see. That's this one. Which one? With PD. With PD, NH3 taken 6 times plus 4, which means again here 6 hexaamine palladium plus 4 complex. So this hexaamine palladium plus 4 complex will have palladium in plus 4 oxidation state, and atomic number of palladium is 46 minus oxidation state is 4 plus 6 ligands donating 12 electrons will render that one as what? 54, which is again the configuration of xenon. So therefore again this palladium complex is stable, you can say, and follows EAN rule, and you can say Sidgwick's theory is obeyed. And similarly platinum complex, the atomic number of platinum complex is hexachloro platinum 4 complex ion, or hexachloro platinum 4 oxidation state ion. Since it is -2 here, you can say platinum would be +4, because algebraic sum of charges is equal to -2 here. So 6 Cl minus and Pt will be +4, making that one as -2. So from that, electrons lost during oxidation is 4 electrons. So your atomic number -4 plus 12, making that one as 86. And again here also it is obeyed by attaining the configuration of radon. Okay, so now 1 or 2 complexes where this EAN is not followed. This hexaamine chromium 3 complex, hexaamine chromium 3 complex, where the oxidation state of chromium is +3, and 6 ligands are donating what? 6 amine ligands are donating 12 electrons, making that one as chromium 24 minus 3 plus 12. The electronic configuration EAN would be 35. and you can say n is not followed or not at 10 nearest noble gas configuration, less stable, or you can say Sidgwick's interpretation is wrong in this case. K3 FeCN6, K3 FeCN6. So again, three counter ions are there, 3K plus counter ions are there. So from that you can say Fe is plus 3. Fe atomic number is 26 minus oxidation state is 3 plus 6 cyanide ligands will render 12 electrons, making that one as what? 35. So again here also what you can say, that EAN is not followed. EAN is not followed, you can say. So if EAN is not followed, Sidgwick's that is not complex is less stable, you can say. Similarly, in the case of nickel with hexa coordinated amine plus 2 ion, hexa amino nickel 2 ion, you can say, this one, the last one, and oxidation state is plus 2 here, and electrons lost in ion formation is what? 2. So then what you can say, nickel atomic number is 28 minus 2 plus 6 ligands will donate 12 electrons. The sum of these will become equal to what? 38, which is beyond 36. Then you can say this is also not attaining what? Next nearest noble gas configuration. If it is not attaining next nearest noble gas configuration, what you can say is that the complex is not stable, or EAN is not followed. That's how this EAN is interpreted. And here also there are some, what you can say, certain limitations are there. Certain limitations are there. So what are the limitations where this theory has couldn't answer about the complexes? Where which part of the coordination compounds science is not explained, that it couldn't explain what bonding again. So why there is again here in square plane they are coming at right angles to each other, that part is not explained. The bonding part is not explained. The covalent nature of this bonding is not explained here. Color properties, magnetic properties, also again you will cite the same. Whichever the answer is not there in EAN rule, that we will write here as what? Limitation. Energy aspect and stability of for non-EAN rule followers. Certain complexes are not following EAN rule, but still they are stable, truly speaking. So why non-EAN rule follower molecules or complexes is having stability? That also is not explained by what? Your Sidgwick's theory. So that couldn't explain. These things they will ask in examination. That's why we are writing here limitations part. Explain the limitations of Sidgwick's theory. Explain the limitations of Werner's theory. That he would ask. So couldn't explain what? Bonding properties and properties of complexes is not explained. Color properties of not complexes is not explained. Magnetic properties, optical properties are also not explained here. Energy aspects and stability of complexes is not explained by what rule? EAN rule. That we should keep it in mind. So then we will move on. If that is not explained, then which theory would explain that? That is answered by what? Our next theories to follow up. So what are the theories that we are having more? We have seen Werner's theory, which has given a slight indication of about how to write the complex formula. And now we have seen electronic interpretation of molecule in the form of EAN rule. And then comes up with the next theory, that is valence bond theory. That would explain us. So the next theory is what? Your valence bond theory. The valence bond theory would explain the covalent nature of this coordinate covalent bond. So this one we have seen in inorganic chemistry also, wherein hybridization occurs, and then what happens? Hybrid orbitals are directed in space in certain directions, and because of that what happens? The resulting molecule will have certain geometry. That we have seen in valence bond theory. Now this valence bond theory would answer us the directional nature of this covalent coordinate covalent bonds. The coordinate covalent bonds are having what? Covalent nature. They may be sometimes sigma, sometimes pi, and because of this explanation, Linus Pauling was awarded Nobel Prize. He was bestowed with the Nobel Prize for this theory, and he is one among many scientists who got 2 Nobel Prizes. Okay, so for this theory, valence bond theory, Linus Pauling got what? Nobel Prize, and this would answer us the directional nature of what you have studied that earlier. There is square planar structure, and we have seen in the today's class, in the starting of that today's class, I have shown you what square planar structure, square, and similarly tetrahedral nature and octahedral structures we have seen. Those are explained the starting of that. So in the very first, this is square plane, octahedral and tetrahedral. How, why they are, why the ligands are approaching in octahedral direction, why the ligands are approaching in tetrahedral direction, why the ligands are approaching in what, a square planar direction, that is answered through this theory. What is that theory? That is your Linus Pauling's theory, that is valence bond theory. This valence bond theory would answer us. So what is the, why he got, I told you that he got 2 Nobel Prizes. One is for Nobel Prize in Peace, and another one is for explaining this valence bond theory. Very few got these 2 Nobel Prizes. That's a rarity also. Another one, even Marie Curie got that 2 Nobel Prize, one in chemistry and one in physics she got. And the motive behind giving this Nobel Prize in chemistry is he could explain the chemical bond in inorganic chemistry, nature of that chemical bond he has explained. And this has given us a tremendous work has been carried out by using nature of chemical bond and directional properties of chemical bonds. And from directional nature of chemical bond, what happened is we could able to understand the structure of molecules, and from structure of molecules many things has opened up for us. So we could understand the structure of molecule. From structure only many things could be answered. Why certain molecules are oriented in direction, why not in this direction, why not, all this could be answered by using what, structure of molecules. So that theory we are going to see. Okay, so as valence bond theory. So that valence bond theory we're going to look in the next session. Okay, thank you.